Yeah, I mean, so thank you everybody for coming. It's a really great pleasure to be able to talk to you in person. And I mean, I should point out, like in the introduction, I just finished my PhD, and this is one of the first times I've ever heard my name said as Dr. Ryley Hill. So that gave me a little bit of a jump at the beginning. I was like, whoa, wait a minute, that can't be me. But yes, no, it is. All right, so you've probably heard a whole lot of things about the James Webb Space Telescope in the news. This is probably one of the most ambitious missions ever carried out by astronomers. This telescope alone cost about $11 billion. It was delayed and delayed. But now that it's been launched, I would like to share with you some of the awesome things we've been learning about the universe, and in particular, things we're learning about galaxies at the beginning of the universe. And so, just to kind of get ourselves oriented, I want to, just explain what scales we're talking about here when I talk about galaxies and when I talk about, the size of the universe. So, here we are, humans. We live on a planet called the Earth, and the Earth is a planet in the solar system. We all orbit the star, which we call the sun, and the various other planets. And our planet, Earth, and the sun here, is just one star in a galaxy full of billions of stars. In fact, there are about 10 billion stars in our galaxy, which we call the Milky Way. But when you are thinking about, how things come together in the universe, galaxies are not actually the largest things in the universe. The largest gravitationally bound objects in the universe are galaxy clusters, which are groups of typically about 1,000 galaxies, all gravitationally bound to each other. And for us, humans living on a planet called the Earth in a galaxy called the Milky Way, our Milky Way galaxy is part of a galaxy cluster, which we call the Virgo galaxy cluster. And so when I talk about galaxies and galaxy clusters, these are the sorts of scales we should be thinking. We have, stars with various planets orbiting them, galaxies made of tens of billions of stars, and then galaxy clusters made of thousands of galaxies. So, of course, these objects are very, very huge. I mean, sometimes you hear in the news things like, the size of the galaxy is this many billion tennis courts across. But of course, you can't picture in your what billions of tennis courts looks like. So it's a little bit hard to imagine these scales. But we can still put numbers to them, and we can still understand them. And so that's what my research is about. The next thing that I would like to introduce is just a quick timeline of the history of the universe. So we now know that the universe is about 13.8 billion years old. So over here on the right-hand side of this diagram, these are galaxies like our Milky Way here, 13.8 billion years after the Big Bang. But with the James Webb Space Telescope, when we talk about looking back to the beginning of the universe, looking at the first galaxies, we're talking about periods around here. So the first galaxies in the universe would have emerged when the universe was about 100 million years old or so. So that's 100 million years old compared to where we are today at 13.8 billion years. And so between that time, between when the first galaxies emerged, 100 million years after the Big Bang, up until today, galaxies underwent quite a lot of changes. So they formed their stars, they started to cluster into these gravitationally bound galaxy clusters that I told you about, and various other astrophysical processes would have occurred over the course of 13.7 billion years, up until we get to today. And so what my research focuses on is figuring out, how did the universe go from this period here, from the very first galaxies that emerged shortly after the Big Bang up until today? Because back then, at the beginning of the universe, the universe was full of just hydrogen, and there weren't any stars, there weren't any galaxies, and yet here we are today in a universe full of stars and galaxies. And so understanding how the universe transitioned from this phase up until today, there are lots of things that we don't really understand about how this happened. And so, one of the things you can do to get a handle on how structure emerged and how galaxies emerged is to run computer simulations. So up here, I'm just showing you a couple of snapshots from a computer simulation of a galaxy cluster, what a galaxy cluster would have looked like shortly after the Big Bang and what a galaxy cluster would look like today. And we can learn a lot about how galaxies grew and evolved with our computer simulations, but they don't tell the full story, because in real life, galaxies are much more complicated than you can ever dream of simulating in computers. If you wanted to simulate a single galaxy up to all of its gory detail, you would need the biggest computer that we have available, and you would need to run it for the age of the universe, and more. So there's no way that we're ever going to be able to fully simulate galaxy growth from the beginning of the universe up until today. So, with that in mind, the other approach that we can take to learning about how galaxies grew and how galaxies evolved is to actually look at them with our telescopes. And the way that we can do this is by, the further back, the more distant galaxies that we observe, the further back in time we're looking. So one way to think about this is if I look at a galaxy that's 0.1 billion light years away, that means that we're seeing that galaxy, 13.8 billion years after the Big Bang. If we look at a galaxy that's 10 billion light years away, we're seeing that galaxy as it existed, roughly 3.8 billion years after the Big Bang. So the farther back, the more distant galaxies that you see, the farther back in time you're looking, up until, if you could find yourself a galaxy that was as far as 13 billion light years away, you would be seeing a galaxy as it appeared shortly after the Big Bang. And now the problem is this is still really hard to do. Finding galaxies that are 13 billion light years away is just really hard to do because they're so faint and they're so tiny and so distant. So even telescopes like the Hubble telescope has a hard time spotting these galaxies. But this is exactly why we built the James Webb Space Telescope, is to see these galaxies, these very, very, very distant galaxies, see these galaxies as they appeared shortly after the Big Bang. This is one of the main science goals of the James Webb Space Telescope. So I'm just going to quickly go through what it is about this telescope that makes it so much better than previous telescopes. So for one, this mirror here is the largest mirror ever flown in space. It has a diameter of about 6.5 meters. And so just for comparison, the Hubble Space Telescope's meter is about 2.5 or 3 meters or so. So it's like half the size of this or less. Other telescopes that have flown in space have had mirrors that are even as small as 85 centimeters. So, so yes, this is quite a massive mirror, and so with the larger mirror comes better resolution. You can make sharper images. So the images that are being taken by the James Webb Space Telescope are some of the clearest that we've ever been able to make. Another aspect about the James Webb Space Telescope that makes it really great is that all of the instruments are very, very cold. This is 7 degrees Kelvin, which is, negative 200 and whatever, 50 degrees Celsius. I mean, the instruments on this telescope are very, very, very cold. And the reason why you want your instruments to be cold is because the colder your instruments, the colder the detectors, the cameras, the more sensitive they are to the light. There's less noise coming from the telescope itself. So on top of this ginormous mirror, there is also a bunch of liquid helium in this telescope that keeps the instruments cold. All right, so another thing to point out is that the James Webb Space Telescope it observes infrared light. So this is kind of like the light that you would see in spy movies where they set up these infrared cameras to catch the bad guys as they come in during the night. The same types of detectors, the same types of cameras are on this telescope. And the reason why you want a telescope that can see infrared light is because more distant galaxies emit more red light. This has to do with the expansion of the universe. And we can so this the detectors on this camera, on this telescope, all of these cameras are like made specifically for detecting really distant galaxies. And then lastly, I'll talk about this a little bit more in a bit, but the James Webb Space Telescope is actually orbiting the sun quite far away from the Earth, so it's quite far away from the Earth, and that's beneficial because there's less, well, for one, there's less light pollution from the Earth itself getting in the way of James Webb Space Telescope's cameras. Also, it makes it easier to shield the sun, and it also gives you the ability to see more deep space. And I have a diagram to kind of explain this in a little bit. But all these things combined really make this telescope quite an improvement compared to like Hubble or any of the other space telescopes that you might have heard of. Okay, and I just want to quickly go over some of the different cameras, the different detectors that are on this telescope. The main point here is that the James Webb Space Telescope has both imaging cameras. That's really the same thing as your cell phone. You just take a picture, the shutter opens, collects some light, the shutter closes. And then it also has the capability of doing spectroscopy. Spectroscopy is this tool that astronomers use to measure the brightness of objects at a whole bunch of different wavelengths, and you can study how that brightness varies across wavelength. And that tells you interesting things about the astrophysics going on in your objects. And then lastly, I just want to point out that this FGS camera, this is the Fine Guidance System, was actually built here in Canada, which is our contribution to the James Webb Space Telescope. So there is Canadian technology up there on the James Webb Telescope that's helping and it helps the telescope stabilize and point very, very precisely, and it also helps the telescope know where the Earth is so that it can send data back to the Earth, which is, of course, incredibly crucial. Without this Canadian contribution here, the telescope would not be able to work. Yep, you have a question?
What does FGS stand for?
Fine Guidance System. So it helps guide the telescope. All right. So the James Webb Space Telescope was launched actually on Christmas Day 2021 from French Guiana, and so we just have I have a quick video here showing the launch. You can hear they're speaking in French because this is French Guiana, which is actually And so during this moment here, all the astronomers in the world were biting their nails. It was quite a nervous time.
Decollage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Yes. So you might think, Christmas Day, would there really be anybody there in French Guiana watching this launch? Well, it turns out that there were actually 3 Canadians at this launch. And I don't know if this time of year rings a bell, but this was also like at the beginning of the Omicron, and everything was just going crazy, and so there were only like a couple dozen people in French Guiana for the launch of the biggest telescope ever built by people because of COVID and Christmas, and so I think it's worth pointing out that out of those dozens of people, there were still 3 Canadians. But yeah, and the launch was actually so successful that the James Webb Space Telescope is actually going to be able to observe in its orbit for quite a few years more than it was expected. And that just has to do with the fact that it required less fuel than they thought to get it to where it needed to go because the launch went so smoothly. Okay, so where is the James Webb Space Telescope now? So just for reference, this is where the Hubble telescope orbits. It actually just orbits around the Earth, quite close to the Earth. And this is why you can see James Webb is much farther away from the Earth, so you can see that it has quite a lot less contamination from light pollution from the Earth being farther away. But also, because the Hubble telescope is so close to the Earth, it can only see a small fraction of the sky at a time, whereas the James Webb Space Telescope, way out here, it can see all this deep space. So you have a much clearer view and a much wider view of the deep space out where the James Webb Space Telescope is. And just in case you're curious, this spot here is called L2. It's the second Lagrange point. So when you put an object at L2, it will orbit the sun at the same rate as the Earth orbits the sun. And so you maintain this sort of nice symmetry so that James Webb Space Telescope could always see the Earth. And the Earth is always partially blocking the sun, which is good. Yes, you have a question?
The Hubble telescope is still operating.
Yes, the Hubble telescope is still operating, but it is definitely on its last leg. So it's going through its 26th year, I think, of observations. Yeah, question here?
About the Hubble, and because you're talking, well, you're saying that the Hubble is, already coming, its life is coming to an end.
Yeah.
When do you think it'll just be totally inoperable and just slowly just orbit into the Earth and crash in the atmosphere somewhere?
How much longer does the Hubble have?
Like when does
maybe
it just spiral into the atmosphere?
Yeah,
and
so
disintegrate?
so the first thing that will happen to the Hubble is the cameras will stop working, and once the cameras stop working, then they will probably then the Hubble will start to spiral down and burn up in the atmosphere. And I mean, it has, if you're optimistic, maybe another 10 years, pessimistic, another couple of years. I mean, we'll see. Okay. Yeah, one more question?
Approximately how long does it take for the Webb to send a signal to Earth to receive the...
Oh, it's not that. It's like dozens of seconds. It's not. So it's 1.5 million. This diagram here is actually to scale. Seconds, maybe minutes. I would have to think about it. So the speed of light is 3 times 10 to the 8 meters per second. This is in. Anyways, it's not like a very long time. So Mars it takes quite a long time, hours. But here it's not super long.
So everybody, for general questions like this, there will be lots of time to ask them at the end of the talk. So we could let Ryley carry on and come back to those.
Yes, but I really
Thank you for hold on to that. Don't forget.
Yes, please. I do want to hear your questions. Okay. So I just want to show you this video quickly. This is a simulation of how the James Webb Space Telescope sort of unfurled when it reached its L2, when it reached its observing point. So the telescope was not sent to its final destination totally, put together and ready to go. It was all squished up, folded up, compact in order to make it easier to launch it on a rocket. And so, I should point out that all this complicated business is happening 1.5 million kilometers from space, and if one thing goes wrong, it's done. Like, you can't send a person out there to fix it. No human has ever gone beyond the moon. This is like 5 times farther than the moon. So the astronomy community was like, really like, oh my gosh, this is really intense. If something goes wrong, we are totally done. This was quite nerve-wracking, just watching this happen just after launch. I think this part here is probably the most difficult step. So these mirrors are, incredibly fine-tuned, very, very, very smooth, and they needed to unfold perfectly. But, it was a success. Nothing went wrong. I'm happy to say that, the telescope was launched perfectly, better than expected, so it has even more time in its orbit to make observations. All these components unfolded successfully. You'd think, normally with missions like this, at least one thing goes wrong, but so far we haven't figured out what that one thing was, so it's been pretty good. Okay, so now, I've talked to you a lot about the telescope itself, but I think it's time to actually see some nice pictures that the telescope is taking. Oh, right, no, I had this one first. Sorry. Just a quick timeline, just to get an idea of, how this telescope will be operating over the next, 10 years or so. So after the telescope made it to its observing site and opened up and everything, there was a commissioning phase, so the people at NASA had to do a whole bunch of checks to make sure everything was functional and online, and they took the first images and started, doing more precise alignments of the mirror and everything. So that took about 5 or 6 months. And then after that, the telescope started it started carrying out these early release science programs. So back in November of 2017, I believe it was, the James Webb Space Telescope folks asked the astronomy community to submit proposals for things that we thought would be really good science targets to figure out how the telescope would operate. So these are things like, looking at Jupiter, just make sure that it looks like what you think Jupiter should look like, things like that. So these programs have been carrying out all throughout the summer. They're nearly completed. So I'm part of a collaboration that had a program on here, and I'll show you some data from that at the end. So after this sort of early phase where we've been making sure that the telescope's working, making sure that we understand all the instruments, What's going to happen now is the telescope, every year, the people who run the telescope are going to ask us, the astronomy community, for us to submit programs, observations that we would like the telescope to carry out. So once per year, this year it's in January, all of the astronomers around the world submit proposals. We say, hey, if you point the telescope at this galaxy, I'm going to do this science, I'm going to calculate this, I'm going to learn that about galaxies, so on and so forth. And there's a committee who looks through all those proposals and figures out and decides, which ones should be done. And that's how this telescope is going to operate up until it runs out of fuel. So every year, we're all going to get together, all the astronomers are going to get together and think about what it is that we should observe with the telescope. We're going to write up our science case, justify our observations, and then have them accepted or rejected by this committee. And so that's what's going to be going on now. I guess it's also worth pointing out that these first science observations that the telescope has made, they're made public immediately after being taken. So you could log in to your. I mean, you don't even need to have university credentials. You can just go to the NASA website, follow some links, and download actual James Webb Space Telescope data, and open them up on your computer and have a look for yourselves. Everything that's being taken right now is made public right away, and that's just to help the astronomy community come together and build tools for analyzing the data. Because this is a new telescope, we want everyone to work together to figure out how the instruments work and make tools for the community to reduce the data and maximize the amount of science output as quickly as possible. But in the future when we write proposals, we're going to have a year to play with the data ourselves before it gets made public. Okay, so yes, now I'm going to show you pictures from the James Webb Space Telescope after talking about it for all this time. Okay, so here's a picture that you might have seen. This is Stephan's Quintet, or as I like to call it, the Hickson Compact Group 92, because this is Paul Hickson, who is a member of the astronomy department here at UBC, just down the road. So Paul discovered this group of galaxies. So there's a Canadian connection to this as well. So this is a group of 4 interacting galaxies in the nearby universe. These galaxies are not too far from our own galaxy. In fact, they're part of the same larger galaxy cluster that we live in. But this is one of the sharpest images that we have of this group of interacting galaxies to date. And then, it's also worth pointing out that there's, all these little points in the back. These are all, most of these anyways, are individual galaxies that are much further away. And so just the wealth of information in this picture is pretty amazing. So the James Webb Space Telescope has also been looking at things inside our own galaxy. So this Southern Ring Nebula here, this is a place where gas is starting to, a big ball of gas is starting to collapse and compress and form stars. So this is a place where stars are being born in our own galaxy. And these observations are going to help us learn about the processes by which gas collapses and forms stars. This is probably my favorite picture from the James Webb Telescope so far. So this is it is a picture, SMAX 0723, a very funny name. We astronomers aren't very good at coming up with names, but anyways, this is a galaxy cluster. One of the things near and dear to my heart because my PhD was about galaxy clusters. Most of the galaxies in this image are all gravitationally bound together, and they form a coherent structure, a coherent galaxy cluster. But you'll notice that, again, in the background there are tons and tons of little tiny smudges. And actually, if you zoom in on a random spot, the number of little tiny smudges in each, even what you would call a blank patch of the sky, is quite spectacular. And so, I would say these galaxies here, all these little tiny faint smudges in the background behind the galaxy cluster, these are actually some of the most distant galaxies that we've ever seen. These are galaxies as they appear shortly after the Big Bang. And so just to kind of walk through one of them, so I know it doesn't look super dramatic. You don't see these amazing spiral structures or anything like that. But in any case, this little smudge here, which was discovered in the James Webb Space Telescope, this is a candidate for one of the most distant galaxies that we've ever detected. This is a galaxy as it appeared less than 300 million years after the Big Bang. And the reason why we can tell how far away it is actually because each one of these images is a picture from the James Webb Space Telescope taken by a different filter. So that means a different wavelength. This is 1.5 micrometers, 2 micrometers, 2.7, so on and so forth. So as you're going across to the right, these are longer wavelength observations. It's like looking at purple light, then blue light, green light, red light, only shifted to longer wavelengths. And the wavelength, the picture at which the galaxy disappears, you can see it's gone here and then it appears here. That actually tells you something about how far away the galaxy is. So most galaxies in the universe, you would see them in all these ones, but because it disappears in this filter, that means that it's so far away that it must exist at the beginning, like shortly after the Big Bang. And so actually, there are almost 100 galaxies in this picture alone that are, that we think existed shortly after the Big Bang, around this epoch of about 300 million years. And this is the first time that we've ever really been able to study a statistically significant sample of galaxies, this early in the universe, and we can start to learn about, how galaxies emerged, and then compare them to the galaxies that we see today to understand how galaxies grew from the beginning of the Big Bang up until today. And then I just wanted to point out, one of the things that I'm doing with this James Webb Space Telescope data is I've been looking at this, a similar region, one of these deep images of the space taken by the James Webb Space Telescope, and I've been taking data from another telescope called the ALMA telescope, which observes at radio wavelengths. And I've been stitching together a picture of the same patch of the sky, but seen by this radio telescope. And by comparing galaxies that are detected in the radio telescope with the galaxies that are detected with the James Webb Space Telescope, we can learn more things about what's going on with the galaxies. And in particular, we can learn about how they're forming their stars, how the first galaxies in the universe, how the star formation turned on and stuff. So that's what some of my research is going to be about. Okay. So I just mentioned, I'm interested in studying, how the these galaxies in the early universe formed their stars, because this is these galaxies 300 million years after the Big Bang, they're forming the very first stars, and so we're interested in how that process occurred, and that's one of the aspects of my research is about. And so I think it's worth just walking through how exactly these longer wavelength observations help us understand how galaxies form stars. So, we're all used to this optical light. It's what we're all looking at right now. These are photons that have wavelengths. They're short wavelengths of a couple hundred nanometers. But those aren't the only photons out there. There are infrared photons. I mean, this is like your body is always giving out infrared photons because heat emits infrared photons. But even longer wavelengths, we have submillimeter and millimeter wavelengths. That just means the wavelength of the photon is less than a millimeter or about a millimeter. And so it turns out that when you look at a galaxy at optical and infrared wavelengths, what you're seeing in your telescope picture is light emitted directly by the stars. So here's a picture of the Andromeda galaxy, and that you're all perhaps familiar with, and all the everywhere that it's bright, those are just stars. You're seeing the stars directly. But then, if you look at the same galaxy at these longer wavelengths, submillimeter and millimeter wavelengths, you're no longer seeing the stars. In fact, what you're seeing is places where stars are being formed. So the bright spots here are indicative of star formation. And so by comparing this image taken at shorter wavelengths with this image taken at longer wavelengths, you learn first about where the stars are, how many stars there are, and then second, where stars are being made and how fast stars are being made. And those two pieces of information are crucial for understanding how galaxies grew and evolved over time. And so, right. So, and another important aspect to my research is gravitational lensing. So, I'll show this picture again, but you might have noticed that there are some arcs in that picture of a galaxy cluster. Some of the galaxies look like they're bent, and that's because of this effect called gravitational lensing. So, if you have a galaxy, you're looking at a galaxy. Well, okay. So, if you're looking at a background galaxy compared to a foreground galaxy, this galaxy is behind this galaxy, and this is our line of sight. So this is, imagine looking up at the sky. You see this galaxy, and behind it is another one. You can have a situation where the geometry is just right, that the light from the background galaxy actually gets bent around the foreground galaxy, and what you see is something like this. It looks like a ring. So this is very similar to if you hold up a magnifying glass in front of a light. The magnifying glass will bend the light and make it look like a ring. And so actually, this is what it looks like in real life. So these rings out in space are actually galaxies that have had their light bent by something between us and the galaxy. And one of the great things about this effect, about this gravitational lensing effect, is that it not only distorts the image of the galaxy behind it, but it actually magnifies the light of the galaxies behind it. So all these galaxies here are magnified by factors of 10, 20, even 100. So it means you can see really, really, really fine details much better than if the light was not being magnified. And in particular, these images here are pictures of galaxies taken with the submillimeter telescope. And like I said before, the submillimeter wavelengths are tracers of where stars are being formed. So this is a picture of where stars are being formed in these galaxies. And the star formation sites are being magnified by quite a significant amount by this lensing effect. And this allows me to study how these distant galaxies are forming their stars in great detail. The problem is that up until now, we really did not know where the stars were. We could not see the stars themselves because we didn't have a telescope capable of imaging these galaxies at optical and infrared wavelengths. So here on the left is an example of one of these rings. So the blue contours in the back are contours of where the rings are. So you can see, maybe it's this one here or this one here, I can't remember. But so the places where this image is dark is the same as where this image is blue. And the image in the background was taken by a telescope that should have seen the stars, but unfortunately, the stars were just too faint to be detected by this telescope, because this was not taken by the James Webb Telescope. This was taken by the Hubble telescope, and so the Hubble telescope was just not good enough to see the stars in the background. Another problem that we faced before the launch of the James Webb Space Telescope was, there have been telescopes that are sensitive enough to detect the starlight, but the mirrors were so small. Remember I said the James Webb Space Telescope, the mirror is huge, so it can see really, really fine detail. So before that, we had telescopes that operated at infrared wavelengths, but the mirror was like this big. And so that means you can't make a sharp image. Instead, you just get this giant blob. So hidden within this giant blob is the stars that we want to study and we want to learn, and we want to use to learn about how these galaxies evolved. But we just can't tell what's going on because it's just a giant blob. So this is why the James Webb Space Telescope is so exciting. So here, I'm showing you some brand new James Webb Space Telescope data of these gravitationally lensed galaxies. And this is the first time that we've been able to see these rings of starlight. Before, we could only see these rings at submillimeter and millimeter wavelengths, where we were seeing the star formation, not the stars themselves. Now we're actually seeing the stars in these distant galaxies. And so this is quite exciting because now we can learn about, we can piece together both how much stars these galaxies have formed and how fast they're forming their stars, and tell a story about how galaxies evolved over time. And one of the other cool things about these images is you can see not only the background galaxy, but also the galaxy in between us and the background galaxy, the galaxy that's doing the magnification. So before, in this picture, you can only see the background galaxy. You can't see the one in the middle. But here, now we can see both. So this makes it a lot easier to model, model the geometry and pull out how much magnification is occurring, and therefore correct for the amount of stars there are. So this is really exciting. Okay. So lastly, I just wanted to highlight, some of the other things that the James Webb Space Telescope is doing, because of course this telescope was not built only to look at my favorite distant galaxies. It's built to do a whole bunch of different things. And so, as I mentioned before, the James Webb Space Telescope is going to be a really great facility for studying how stars form in our own Milky Way. So here's a picture of the Carina Nebula. All this stuff here is gas, is hydrogen gas, and it's in the process of collapsing under its own gravity. And eventually, the collapse is going to, be so great that stars are going to form. It's going to collapse so much that the gas is going to heat up to the point where nuclear fusion will start happening, and so places like this are places where stars are forming. And with the James Webb Space Telescope, we're really going to get to understand a lot better how stars form in detail in our own galaxy. Okay, another really cool thing, which is completely unrelated to galaxies, is exoplanets. So the James Webb Space Telescope is also going to be a really cool facility for studying exoplanets. So in particular, we're wondering, are there habitable planets outside of our solar system? Are there places with aliens, basically? Although the James Webb Space Telescope is not going to tell us whether or not there are aliens. It can tell us whether or not there are planets out there with stuff like water in the atmosphere. So here's an example of a spectrum of an exoplanet's atmosphere, and all these little bumps and wiggles are indicative of places where there is water. So we now know that this particular planet, called WASP 96b, again, a really terrible astronomy name, we now know that this planet, this exoplanet, which is not, so this planet is not in our solar system, this planet is many light years away, orbiting another star. We know that this planet has water in the atmosphere, which is really cool. And so the James Webb Space Telescope is going to be able to do things like this. It's going to be able to measure the components in exoplanet atmospheres, measure how much water is there, how much nitrogen, oxygen, stuff like that, which we can then compare to how much nitrogen and oxygen and water we have in our own planet's atmosphere, and maybe find a planet that seems like it's pretty similar to the Earth. So these are all really cool science things that the James Webb Space Telescope is going to be pursuing. Okay, so I think that brings me to the end of my presentation. So just to summarize, the very first galaxies in our universe would have emerged shortly after the Big Bang, a couple 100 million years after the Big Bang. And then they grew into the structures that we see today, galaxies like the Milky Way, and understanding how that process occurred, how galaxies went from their first emergence 300 million years after the Big Bang until today is an active field of research, one that I am heavily involved in. So with the James Webb Space Telescope, we're now able to actually see these galaxies 300 million years after the Big Bang, and for the first time really get to know how they emerged and then compare those galaxies to the ones that we see today to get a more complete understanding of the evolution of structure in our universe. And for the first time with the James Webb Space Telescope, we're also going to be able to see not only the places where stars are forming in these distant galaxies, but the places where the stars already exist. We're going to be able to measure how many stars are present in distant galaxies. And again, this is something that has been really challenging in the past, and the James Webb Space Telescope is going to make it a lot easier moving forward. Okay, and that's it for my presentation. Oh, thanks.